The topic is arc length and surface area. We're going to do arc length first, and then I'll show you how surface area relates to the arc length. And if you're following along in the Thomas textbook, this is sections 6.3 and 6.4. As you see, we've actually circled back a little bit to an earlier chapter. It just seems to fall naturally in this place in the course. When we talk about arc length, what we're talking about is, imagine that we have some curve that I've written here. It's just an arbitrary curve that we'll call y equals f of x. And what we want to know is how far we would travel if we walk the length of this curve from x equals a up to x equals b. So uh, what you have to imagine is, instead of simply asking the distance between these two red points, what we're asking is, if an ant were crawling along this curve, how far would the ant have to walk? Or another way of thinking about it is, if we actually had to lay out a piece of string along the purple path, how long a piece of string would that be? So that's the length that we want to compute. Let me before I give you the formula for this, and this really is essentially just a formula that you have to know, um, then let me just show you how we would get to this point. So imagine that we want to find the length of this segment between these two dots along the purple curve. As we often do in calculus, we approximate a length by using a tangent line. So what I've drawn here is, I've drawn the blue line is a tangent line. It's tangent at the point x that you see right here, like that. So let's imagine that we walk a very tiny amount in the horizontal direction to the right. You should be familiar enough with the language of calculus at this point to realize that when we have a very tiny amount of horizontal distance, the name we give to it is dx. So if I walk dx, if that's the tiny amount that I'd be walking horizontally as I follow this diagonal line, the amount that I'd be walking vertically is dy. Now, what you can see is that the distance that I walk, which, well, let me highlight it here, that distance that I would walk along the tangent line is really the hypotenuse of a right triangle. So what you can see is that the length of that hypotenuse, let's just call it L actually. So the length of that hypotenuse is equal to the square root of dx squared plus dy squared. I know you're not usually used to doing things like squaring dx's and dy's, but just bear with me for a moment. So if that's the case, what we want to be able to do is really write dy in terms of things that we know about x. So let's just come down here for a minute. We know that dy over dx is just another way of writing f prime of x. If I multiply both sides of this equation by dx, I get that dy is equal to f prime of x dx. So let's come back up here for a minute and actually substitute that in. Let's write that L is equal to the square root of dx squared plus dy is f prime of x dx, so that's going to be f prime of x squared times dx squared. That's what I can replace dy with. And let me just put an extra parentheses in so it matches. Okay, so now let's factor out the dx squared. So this is going to become L equals square root of 1 plus f prime of x times the square root of dx squared. That's going to equal, once I simplify, that's going to give me 1 plus, sorry, there should have been a squared there, 1 plus f prime of x squared dx. So that's the length of this hypotenuse. The thing is, we're not interested in just one hypotenuse. Really, all I've done here is drawn, a little picture that looks like that. Really what I want to do is imagine that I'm doing this across the entire length of the curve and adding up all the hypotenuses. Well, let's think about how we would do that. In fact, I've drawn a picture here of what that looks like. Here, I've simply drawn a whole bunch of right triangles connecting a small number of points, each of which is dx apart. Well, let's think about how we would write the idea of adding up all of these hypotenuses from a to b in using the language of calculus. We know that we add things up by writing an integral sign. We know that the lowest x value we're looking at is a, the highest x value that we're looking at is b, and we know that the length of these tiny hypotenuses is, going back up here, is square root of 1 plus f prime of x squared dx. So square root of 1 plus f prime of x squared, I don't need to put the dot in, dx. So each of these, excuse me, each of these is the length of a tiny hypotenuse. And we're adding them all up from a to b, so this integral would give us the total length of the curve as we walk from this point up to this point. And why, by the way, is it reasonable to approximate the lengths that we're looking at by these hypotenuses? And the answer is because they're really small. We're letting dx be as small as we want, which means that this hypotenuse really doesn't stray very far from the curve, and in the limiting case, which is always what we're doing when we take an integral, it doesn't stray at all. It's just an infinitesimal quantity. So that brings me to the formula for arc length, and that gives us s is equal to, s is the lowercase s is the symbol we use for arc length, is equal to the integral from a to b of the square root of 1 plus f prime of x squared dx. This is the formula that you have to know. And by the way, if you happen to have x as a function of y, for this, you making the exact same argument, I can do it. I can do it in the variable y. I can also say that s is equal to the integral from a to b of the square root of 1 plus g prime of y squared dy. And of course, that would be, let's see, so I'll just mark this. This is if x is a function of y, and this one is for if y is a function of x. And usually we're doing it in the first case. That's why I sort of put in the second one as an afterthought. But you can do it either way. The only thing you have to realize is that in the second case, we would be looking at a curve that was defined sort of like this, and we'd be looking at a and b along the y-axis and asking what the length is of the curve defined like that. This is a drawing of the second case. I've already drawn the first case. So there we go. That's the formula for arc length. If you remember nothing else about arc length, this is the thing really to remember.